In this lab, we will examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. This motion contains some of the behaviors we see in the extreme rope sports example. While motion like this appears complicated, we will find that we can understand and predict this motion using the same techniques and fundamental principles explored in our video lectures. Note that in your analysis, the values of the calibration length, time between video frames, and relevant masses are the same as the vertically oscillating mass discussed in the video lectures. Here in Tracker, we use the same calibration stick and axis orientation as in our video lectures. We plotted every point along the rotation, and we save these points into a CSV file by copying them and putting them into Excel. Start the computational model you constructed while following along with the video lectures. Make the necessary modifications to the model, the motion you just analyzed in this new video. When you have your model working, compare the model predictions with your analyzed data. In particular, you should compare the display window, the predicted motion, and the observed motion of the mass. Plot the graph window, the energy changes you compute in the model, the change in kinetic energy, the change in gravitational potential energy, the change in the spring potential energy, and the change in the total energy. Here in VPython, we have the code from our video lectures that I have modified for this lab. I added an extra graph so that we can see the energy principle and the position in X and Y axis. Here is the second ball to show us our observed motion. This is the mass of the ball and the initial positions of the ball. Here's our spring constant and all of the code discussed in the video lectures. When we run our model, we see that the predicted motion and observed motion are quite a bit off. And as we progress further into the motion, they seem to become further and further apart. There are a number of different variables that could account for the difference in position. The first I have thought of is the mass of the spring. We did not account for the mass of the spring, so here I tweaked the mass of the ball to add the mass of the spring. The second we did not account for is if the ball may have been thrown a slight bit. Finally, we did not account if the video was too dark and skipped any frames. These three new values were just found from experimentation. When I run the Python program now, we'll see the difference. Now we can see the predicted and observed motion is almost identical. What does it mean? For your model, is the energy principle satisfied? Justify your answer by briefly discussing your plots of energy changes. Here we can see that our energy principle is satisfied because the total energy is 0. Using the data you obtain from Tracker, make two separate estimates of oscillation periods. First, by estimating the period of oscillation from the X position data, and second, by estimating the period of oscillation from the Y position data. Compare the two estimates and discuss. In order to measure the oscillation period, find the difference in the peaks or troughs of our wave. In Tracker, we can select each trough or peak note the time and subtract the initial time from the final time. These are the results of my analysis. The Y oscillation period is approximately 1.6 seconds, where the X oscillation period is only 1.5 seconds. I would say this is because the drag on the mass by gravity increases the oscillation period of the Y-axis. Thank you for watching my lab.